All right, hey guys. So calculation just completed. Um, so let's check out what it looks like. So it went through all 150 iterations. It didn't get down to the required residuals, but the solution should still be good. But we'll verify that. So let's go down, click down at graphics, go to contours, and then we'll set up. So go to check filled. Wall solid, if you remember, wall solid is the wall for the actual aircraft. So this will display static pressure contour on that wall solid, and it will fill in the gaps. So it's not just the contours you're seeing. So it's really small there. So let's zoom in, and there you go. There you see the solution. So red is high gauge pressure, blue is lower. You can see the units on the sides in pascals. Um, so you'd expect that here at the stagnation point, it would be approximately equal to dynamic pressure. So if you calculate that, which I did over here, dynamic pressure, so that's at 18 meters squared, standard density is about 198 pascals. So this is showing 175, and it's not going to be exactly the dynamic pressure, but so it's in the ballpark. So yeah, you can see it gets, as the velocity increases, the pressure goes down. So it looks like a pretty decent solution. Yeah, so let's close out of there. So again, the whole point of this, we're trying to make a drag polar. So let's go get the forces on this and see what we can get. So go down to reports. In the results section, go to reports, and then you see on the sidebar here, select forces, and we're going to set that up as well. So this is why it was so critical that in the meshing section, why we had to distinguish between the boundary and the wall solid, because if we didn't create that name section called boundary, this would just be the single wall, and it would be calculating the forces on everything. So you get a ton of viscous forces on basically the test section, if you will. So, but we can ignore that and just write the forces um, for the what you're seeing here. And before we do that, let's actually change the units so we get them in English units, because I don't know how much the aircraft actually weighs in kilograms. So click units up here and just hit British on the side. And now, so we're getting forces. Don't mess with the direction vector. It's just going to give us a Cartesian. You could have it resolve like for lift if you wanted to, but we're just going to do that in MATLAB later. So for now, let's just print these. And now in the little command window, it printed all the forces. So if you go, not in force direction vector, but up here where forces, you see it distinguishes between pressure forces and viscous forces in XYZ coordinates, and then total forces, so the sum of both of those. So you can see it's predicting like 13 pounds in the positive y direction, so going up, which is basically a lift in this case. Our aircraft is predicted to weigh about like 15 pounds, so it's not quite straight and level, but it's getting there, so it's pretty close though. And then this is like a side force, so honestly it's probably just an error because this is symmetrical, but you can see it's almost zero anyway. And then this negative x is drag. So we wanted to calculate a drag polar. So first of all, the velocity from 18 meters per second is 59 feet per second. So let's quickly run a little calculation for the CL and the CD. So we start with the lift, so 13 pounds, 13.48 pounds divided by Q, so divided by 0.5 divided by 0.002376 standard density, divided by V squared, so 59 over here, divided by 59, divided by 59, and then divided by S, which is 8 feet squared for this aircraft, so divided by 8. And we get a lift coefficient of about 0.4, which is pretty good. You know, cruise should be around 0.3 lift coefficient, so 0.4, pretty accurate. If we want to get the drag, we can just divide here, so divide by 13.48 and times by 2.77, so drag coefficient by 0.08. So there you go. That's what we're looking for. However, we want to get a polar, so we want to get multiple angles of attack where we're going to get different CLs and different CDs. So that's the next thing we're going to set up here. So we can go ahead and X out of that. Well, first of all, what I've been doing, or what I would recommend, is opening up Notepad and then copying in this whole section down here, and just copy that in a Notepad, and then save this on Samba somewhere. So I'm not going to do that. I already have it saved, but you guys should do that somewhere where you can access it from your computer if you want to make a drag polar. So we can close out of this results section and go on to making, so this is saying use the settings because we changed the units. So just use settings for current calculation only. So we'll change it again later. All right, and then we go back to the workbench. We can now, we'll start setting up for the drag, for making a alpha sweep. So let's make a few. So this is 0 degrees. One nice thing you can do here is actually you can make a note so you can remember. So 0 degrees alpha. And then every time you drag one of these, it's making a new standalone system. So let's just make a few of them for now. So to expedite, make this go as fast as possible, because you can imagine if you wanted to do like an alpha sweep of like 10 or so angles of attack, you have to make one for each. So it takes kind of a while. So kind of the fastest way I found to do it is we're gonna load up the like we did before, the Rhino model, and we're going to edit it so that we can quickly load up the geometry each time. But you can't actually do like we did in the last video where you just drag over, because you're actually going to have to edit it each time, because you're going to have to rotate the model to reflect angle of attack. So this is exactly what we did before. So it's kind of repetitive, so I'm just going to try to go through it fast. So create body transformation, rotate body, apply, select, Z90, apply, generate, tools, go to enclosure, when it loads, come on. There we go, enclosure, cylinder, x-axis, 25, 20, and load the enclosure. Oh, my bad, you're not supposed to do that yet. We need to redo that. So we're just going to ignore it for now. We need to make a new, no, we got to delete it. My bad. Before you make the enclosure, you have to rotate. Again, so you do another body transformation, rotate. So we need to do the same body, part 1, apply, axis selection. So we need to rotate along the XY axis. So let's do it like this. XY, because we want to rotate alpha. So XY right there, apply, and then let's start with -6 degrees angle of attack. So let's see what that looks like. So it looks like it actually rotated that a +6 degrees. So this is how the rotation is defined. So to get negative, we want to actually put in a positive here, 6 degrees on the left. So and then we generate that rotation. Now we make the enclosure. Same setting, cylinder, x-axis, 20, 25, generate, and then again we should do that. I don't see it. There it is. Okay, and then we should generate the Boolean to delete, just like before. Subtract out the geometry and generate that. There you go. So yeah, and then you basically just have to do that each time. So actually, one thing that does make it faster is if you can actually save it in Design Modeler, and then you can just import the Design Modeler instead of the Rhino model, so you don't have to do that initial 90-degree rotation every time. So you can see, if you say I did that 90-degree rotation and then exported that model in Design Modeler and saved it, like here I saved it as base 2, I can just load that, and then I can go back into Design Modeler and it's already, you don't have to re-import, which takes like 30 seconds, and you don't have to do the rotation, which takes 30 seconds. So it saves you about a minute each time. So I would recommend doing that. And then this one, you just have to, you'd make another rotation. So you can see it's already rotated 90 degrees. Oh, that's not the right one. Create body transformation, rotation, and then this one, we're going to do the same body. New plane, axis, or XY, and then we're going to do this one at, say, 3 degrees, whatever, and generate that, or, yeah, and so that's for minus 3 degrees, alpha, generate, and then we just do the same thing. So you can imagine us doing that over and over again for however many angles you want. I find it faster to, instead of working on the same model and getting the results for each geometry you make, which you could do it, I find it better to just define all the geometries, then mesh each one, and then solve each one. So yeah, let's say, okay, so that, and once we do that for our entire alpha sweep, then we could start getting a drag polar. So I'm going to skip ahead, and in the next video, you'll see all of these completed and solved, and then we'll go on to post-processing and getting that actual drag polar. So thank you for watching.